You ever heard where the water comes from? The air?
Yeah.
So when you make air pollution, you're going to make water pollution for later.
But you get that extra energy in between.
Oh yeah, well I don't know how energy efficient it is to burn slurry.
Slurry is like, it's not refined at all, so it has like everything in it, so it becomes a lot more pollution.
And it's still 99% water, so the energy content is yeah.
Where does the methane come from when it's forming that?
That's an excellent question. We'll come back to it.
Okay.
Check out this cool photo. Yeah, it's a super cool photo. And you can do this. If you can get your hands on methane hydrate, when you light it on fire, the bottom stays cold, obviously, because heat rises, and the flame will be on top, and so it's melting the ice on top and letting the gas out at the top.
Where do you find that?
You can get it all over the place, and it's totally clean. Feed it to my daughter and stuff. It's all good.
Will you do it? Will you bring it in?
And feed it to your daughter.
Yeah, that's me. That's Ronan. Yeah.
It's like slightly heavier than the wife, because it has all the extra stuff in it.
Yeah, that's an interesting question. I don't know.
Wait, that other photo, the guy holding it, was that you?
No, it wasn't. And by the way, I'm just feeding my daughter Snow. When I made this slideshow, I had just gotten back from Mammoth. So yeah.
Like, did you put it in like a drink and then light it on fire?
Yes.
I guess so.
That's so sick.
Gabe's thinking of a cool drink.
Yeah. Cold Jaeger bombs for everyone.
So the question was, how do you get methane into the ice? And I actually look forward to that question because this is the first time I can introduce a really critical concept in APES. And I have a very memorable way to make sure you'll always remember this. Are you aware that it's true you can light your farts?
Yes.
Because it is. It's true. You really can. Yes. Second of all, can you light your burps?
Depends on your diet.
Who's got a lighter?
Anybody have a lighter?
Oh, yeah.
Yes.
Why didn't that light?
Just air is like right here. Hasn't gone through the metabolic process to get the gas to release. It's just like air trapped in here.
First of all, there's all sorts of burps. But even when the burps are truly spontaneous and they're the result of decomposition in your stomach, you still can't light them. Does anybody know where the bubble that becomes a fart is made in your body? Yeah, your colon and your intestines. Does anybody know where the bubbles that become a burp are made in your digestive system? Stomach. What is the difference between your stomach and your intestines? They all have bacteria, but the bacteria are different because one is aerobic and one is anaerobic. The next time you get to find a victim to snuggle with, if you lay on someone's tummy and they're moving around, you'll hear that the stomach is sloshing. There's stomach acid inside of a big bag with air in it. You know, if you're kind of sick or whatever, you might even feel that air moving. So, remember, your stomach is aerobic. There is air. So, when your carbon compounds decompose with air around, the carbon gets stuck to oxygen, and you make CO2, and you can never light your burps because CO2 is not flammable. But in your intestines and colon, there is no air. unless you've been doing some really funny business, there should be no air in there. Hey, I don't judge, whatever. But there's no air in there. So when carbon compounds decompose in your intestines, your colon, that carbon has no oxygen to stick to, it'll stick to hydrogen. So look at this difference. And this is a critical detail. This will come up all year. You must know this. Write it wherever you want to. Anaerobic decomposition gives you methane. Aerobic decomposition gives you carbon dioxide. You can tell there's air because look at the oxygen. That had to come from somewhere. So now, where do we have decomposition and ice formation without oxygen? Bottom of the ocean, or
Space. Under like the ice. Where it caps.
and in the permafrost. Permafrost, you get decomposition without oxygen and ice formation. So if you look up here, please, you see that those green squares, that yellow one, most of the stuff on land. Here, you've got it on land, but that's like alpine tundra, so high elevations. And if not, it's on the continental shelf, right where a bunch of organic material will fall into really deep water. So you've got decomposition without oxygen and ice formation. You'll get methane hydrate. It's a ton of energy. You can light it on fire, which means you can make steam, and that means you can spin a turbine. It's an energy source, perfectly reasonable. The only challenge is, how the heck do we drive around a bunch of ice without it melting?
Really good.
Yeah, Japan had like a really famous experiment. They went to someplace north of Japan, grabbed a giant glob of iceberg that they knew had methane hydrate, tied a chain around it, dragged it into the Sea of Japan, and by the time they got to the dock, they were just dragging a chain through the water because the iceberg melted. As an energy source, it doesn't seem that viable. You know, you can't afford to carve up the permafrost. You can't make like a giant funnel above the permafrost. There's really no way that people can make this into useful energy, but I've got some other interesting facts. There's enough methane trapped as hydrate to multiply the current climate change by 10.
Nice.
Meaning all the climate change that we have seen so far would be one order of magnitude greater if all the ice melts. And I wonder if there's any reason why the ice might be melting. This is the classic positive feedback. This is like the one most memorable, most famous, and most obvious positive feedback loop in the climate cycle. The planet gets hotter, the permafrost starts to melt, which releases methane, which is a global warming gas. That makes the planet hotter, so you melt more permafrost, so you release more methane. This is the biggest positive feedback in the whole climate thing. If we have a way to get it, then it's free energy, whoopee. And if we can't figure out a way to get it while the planet's getting hotter, we've just put a brick on top of the gas pedal and we're getting ready to drive off the pier. Yeah.
So obviously, like methane and CH4 is like greenhouse gas when you burn it and you break the bonds between the carbon and hydrogen. Is the carbon just forms CO2 in the atmosphere and the hydrogen just go into like water vapor? sulfur.
Yes,
So,
they both oxidize.
so then would that cause like overall less or relatively the same like greenhouse effect as if you were?
Cause much less, because certain molecules cause more warming than others. There's this principle called wobble, which is that the bonds between some atoms in a molecule can hold energy. They can be destabilized by an input of energy. So if you take CO2 and you give it heat, the molecule will absorb that heat as energy, and the oxygens start to go like this. Eventually, those oxygens will come back into stasis, and then the heat will be re-released. That's the definition of greenhouse gas, storing heat. This wobbles 10 times more than that. So this is 10 times hotter than that. It makes sense to burn methane.
So like increasing our methane burning used energy sources would decrease like our greenhouse gas.
So releasing all the methane into the atmosphere would be much hotter than burning all the methane and releasing that CO2 instead.
Right.
That's why when you drive down, the methane's on fire.
Yeah.
By Rincon?
Yeah.
Because A, it's toxic, but B, even if it gets to the atmosphere, the methane's way worse for global warming than the CO2.
So the stuff that's evenly centered, I feel like really good at 2 ways to find it.
Yeah, like a really good global warming prevention system would be to light the tundra on fire. Yeah, but like it actually is better than the alternative. I mean, it just boggles the mind that these are the choices we're left with. But yeah, that's kind of where we are.
Yeah.
Okay. Number 22, we just finished. Number 23, I gotta warn you, is a really long list. Now, some of you have done the homework, but in addition to what was in the homework, we have more content. Number 23 is what are the effects of oil and gas extraction plus usage? And I kind of have a chip on my shoulder because I teach environmental science. You'll have to humor me, but you should understand where I'm coming from. The debate is always so narrow because we're so good at shopping that we don't usually think about where things come from and where they go. For example, people say, natural gas, it's so clean. And it is, right? Remember that it can't hold any impurities? So people are like, it's the cleanest fossil fuel. We need more natural gas. The point I'd like to make with number 23 is you can't just focus on what happens when you burn the fuel. You have to remember that that came from somewhere. So, number 23 is all the other stuff that's bad for the environment before you light the fuel on fire. Number 1, the footprint of extraction. How much habitat do we destroy with the wells and the rigs and the roads? And I got to remind you of something. There's a really key detail in this debate. When you ask the oil executives, how much land will you destroy in Anwar? They say 2,000 acres. When you ask the hippies, how much land are they going to destroy? The environmentalist types say 1.5 million acres. How can they both be right?
Direct effects.
Exactly. It's called the virtual versus the actual footprint. You see, if there's a rig over by those dudes, and there's a rig over by these dudes, and they're connected by a road, the actual footprint is the size of that plus the size of the road plus the size of this. Do we agree? The funny thing is, for wildlife, they don't want to be over here or over there. That's called a virtual footprint. When you make an oil field, you've got thousands of wells. Nobody wants to be in between the wells either. The oil executives, they're only measuring